Good evening, dear students. Today's my topic of discussion will be the Mayer theory, and the notes of this topic is based on the book Real Analysis written by H.L. Rodin and P.M. Peasantry from the fourth edition. So I will Dr. Bharat Goel from Khalsa College Patiala welcome you all. So the chapter one is Lebesgue Mayer. So let us discuss some basics of this chapter, what we need to do and what we have to find and what we have to discuss in this chapter. The present chapter throws light on the concept of length of intervals. Obviously, we all know what is the length of an interval. It is obviously the last point minus first point. For example, if the interval is AB, whether it is closed, open, semi-closed, it doesn't matter. Its length will be B minus A, but it is the concept only valid up to the intervals. Now, what about the sets? If we have a set, then how we define its length or how we measure a set? So, in this chapter, we will focus upon the measure of a set. So, by defining a measure on the class of sets on the real line, which includes the intervals also, definitely the concept which is already existing, the length of interval will not be disturbed. It will remain as it is, but we will be able to define the measure of the set after the end of this chapter. The principal goal of the chapter is to introduce Lebesgue measurable sets and to verify its properties. At the end, we shall construct non-measurable sets in real numbers. So this is the some goal of our chapter, what we need to do in the whole chapter. So let us start the chapter. So firstly, the length of intervals definition. I already told you the length of interval is defined as the difference of endpoints of the interval if interval is bounded, and infinity if interval is unbounded. The interval can be A, B, that means open interval, closed A, B, closed open, or open closed. Here A, B both being finite numbers, each interval will be of length equal to B minus A and is denoted by length I. This is the symbol length I, where I is the interval. So, some points we need to consider after the uh, knowledge of this definition. Length is an example of a set function, that is a function in which each set is associated with an extended real number. So, length is basically a function in which you have input a set and you have got a real number. For example, if you input the interval 1, 5, so you will get the output 5 minus 1, that is 4. So it is a function whose input is the set and output is a extended real number. Why extended? Because the interval may be of infinite length also. So in the further discussion, we extend the set function length to a collection of the sets of real numbers. So obviously, we will increase our domain. In the above definition, the domain is only the collection of all the intervals. But in the further discussion, we will increase our domain. We will extend the set function length to a collection of the set of real numbers. And then we will construct a collection of sets called Lebesgue measurable sets and a set function of this collection called Lebesgue measure, which will be denoted by n. So then we will construct a special class, which that class will be known as the class of Lebesgue measurable sets. So Henry Lebesgue is the name of mathematician. So he has defined a class of the sets which is called measurable sets, and that class, according to his name, will be called as Lebesgue measurable sets. And obviously, we will define a measure for that set, and that measure will be called Lebesgue measure, and it will be denoted by M. So we need to verify the following properties. We target these three properties for the Lebesgue measure M. The measure of an interval is its length, obviously, because the already existing concept will should be remain same. So measure of an interval should be the length according to that new measure also. Measure is translation invariant. That means if you shift the origin, then it doesn't vary. Measure is countably additive over countable disjoint union of sets. So measure is countably additive means if you apply measure on the union of disjoint sets, then it will be equal to summation of the measure of the sets. But it is not possible to construct a set function that possesses the above three properties and is defined for all sets of real numbers. Yes, it is a very typical task, but I think it is not possible also because measure is countably additive. That property somehow will disturb us. We will see in the next lectures also. So above three properties cannot be verified generally. So we need to define a class of sets. So our goal will be we respond to this limitation by constructing a set function on a very rich class of sets that possesses the above three properties in two states. So our goal will remain on the this concept that we must construct a set function, the Lebesgue-Meyer M, but it will be verified upon a rich class of sets, not on all the sets. But that class that we will define is also very rich. So in the first stage, we will construct a set function called outer Meyer denoted by M star, which satisfies the above defined first two properties in the same form as defined. Firstly, we will start our discussion from the definition of the outer Meyer, and that outer Meyer will be denoted by M star. And it will definitely satisfy the first two properties. The Meyer, outer Meyer of an interval is the length, and outer Meyer is translation in wavelength. But that property, that outer Meyer function will not satisfy our third property. It will only satisfy it up to countably sub-additive. So countably sub-additive means we have inequality in the place of equality in that property. We will see it in the further lectures. All the three properties will be discussed separately. Then in the second stage, because the third property is not verified, so we will define a class of Lebesgue measurable sets, and then we restrict the set function M to the collection of Lebesgue measurable sets and denote it by M star. Then when we restrict our set function, here we have M star to the collection of Lebesgue measurable sets, and that restricted function will be denoted by M, and we will prove that this M is also satisfying the third property. So thank you very much.